here, and I'm so glad to give a talk in KAIST. So today I will talk about the structural stability of meandering-hyperbolic group actions. So this is first, we just start with this project to fill some details of the Sullivan's paper about the hyperbolic group action, characterizing convex co-compact group in hyperbolic geometry. But after that, we realized that our statement filling the details can be developed to some theory of the isometric representation in general symmetric space, and then also apply to some uniform lattice in higher rank semisimple regroups. So anyway, so we are still developing our theory to non-hyperbolic group actions, including the projective space. So I'm so glad to give a talk the ongoing project here. Okay, so this is joint work with Misha Kapovich and Jae-Jung Lee, and let me first give the definition of structural stability. Okay, so let the gamma be the subgroup of regroup G. Then we say that the gamma is structurally stable. If all sufficiently near representation of the gamma into the G are injective. So here the structural stability involves some injectivities, some algebraic property. But the 1985, the Sullivan proved that. So he had some question in mind, what is the equivalence of structurally stable groups in PSL to C. So he proved that the structurally stable finite general subgroup of PSL to C is either rigid. So rigid means that there are no deformation, or the convex co-compact group. So that means that almost the structurally stable the group is equivalent to the convex co-compact groups. So, but he used some geometric group theory to prove this theorem, and also the many geometric group property about the hyperbolic groups has been used. So okay, so what is a convex co-compact group? So convex co-compact group is defined by the third and fourth, but here we just give a definition of convex co-compact group in the isometric group of hyperbolic n space. So this subgroup gamma is a convex co-compact group if there is some gamma in the convex subset of hyperbolic n space, so only the gamma action is co-compact. So the picture looks like this. So this the convex co-compact group has been played important role in developing the hyperbolic three-manifold theory, and also as you know, the hyperbolic n space is a subset of the n projective space, right? So because we are developing our theory to the symmetric space, so you can think of the hyperbolic space as you can think of the hyperbolic n space as a symmetric space, and also you can think of the n space as some subdomain of some boundary of higher rank symmetric space. So anyway, so if you have a convex co-compact group, then the mirror subgramma, that means that the gamma, this group, is isometric embedded into hyperbolic n space. So that means that every convex co-compact group is quasi-isometric to some convex subset of hyperbolic n space. So it has some negatively curved geometry. So Gromov actually introduced the notion of hyperbolicity in group. So every convex co-compact group is a order hyperbolic group, right? So like this. So this is a definition of a hyperbolicity in group. Some metric space is a delta hyperbolic if you draw the triangle, then it satisfies like this. So this property gives a picture like this. Okay, this is some essential property of the hyperbolic space. So if you have the group, then you can have some carry graph associated to the group. So with respect to some symmetric generic set S. So if the carry graph is the delta hyperbolic, then we can say that the gamma is a order hyperbolic group. So as I told you, all the convex co-compact groups are the order hyperbolic groups. And also you can define the boundary. So this is the ideal boundary of the carry graph. So which is the set of equivalence class of the quasi-geodesic ray under some Hausdorff distance equivalence relation. Okay, so then there are many equivalent condition for the convex co-compact groups. So here I just want to mention the perspective. The first, so quasi-isometric embedding of the carry graph of group gamma into the hyperbolic space. So by the mirror of the Sungwoon lemma. And also by using the quasi-isometric embedding of the group, you can obtain the embedding of the gamma action on the group boundary of gamma into the boundary of n space. So this is the first condition. This is a second condition. So you can think of the two actions inside the hyperbolic n space and also the gamma action on the infinity. Okay. So then, and also there are some important property for the convex co-compact groups. So stability, say that. So convex co-compactness is stable in the isometric group of hyperbolic n space. So that means that if you perturb a little of a convex co-compact group, then you obtain still the convex co-compact group. So that means that the condition, that means that the quasi-isometric embeddings of gamma and the embeddings of the gamma action on the group boundary also preserved on the small perturbation of convex co-compact group. So the convex co-compact groups are structurally stable. So if you perturb a little the convex co-compact group, the representation is still the injective. Okay, so this is a perspective of Sullivan for stability of convex co-compact group. So this here is a setup for the hyperbolic group action. So M is a compact CO manifold. This is you can think of the boundary of the hyperbolic n space. So and also the gamma is the finite generic group, and there is some gamma action on M. Okay, and lambda is a gamma invariant compact subset of M. So this is kind of the limit set of gamma. Then Sullivan defined the action on the lambda is said to be hyperbolic if the first require the action is expanding, and the second, the M-Farrow traveling. So I will explain what is M-Farrow traveling and the expanding. Anyway, so this action will be stable, and also convex co-compact groups action on its limit set is a hyperbolic action. Okay, so here is the expanding action. So expanding action is a very natural. So the action, gamma action on the lambda is expanding. Then there exists some finite symmetric general set S. And also there exists some open cover associated to this symmetric generic set. So, and such that the S1 action, so S1 SI action is inverse action is a lambda expanding on the associated open subset, the UI. Okay. So you can cover, so that means that, there is this is a the green one is a lambda gamma invariant compact subset or lambda, and then you can cover by open set the expanding, which is expanding domain for the symmetric generating elements. Okay, so this is a expanding action. So then if you have a expanding action, then the expansion, the data, so you have a data, the symmetric generated set and the open covers, and this is the expanding factor. Then you can find some encoding. So what is the encoding? So first choose the Riemann number delta of the open cover U. Then for each the point X in lambda, and you can find some sequence of elements of S, like this. So first start with the X. Okay, so first start X. Then, so first choose arbitrary element in S. So then say some S alpha 0. So then you can move the X to X1 by the action of S alpha 1 0 inverse. Okay. So after that, we choose the S alpha 1 such that this X1, the delta ball of X1 is included some U alpha 1. So this is the expanding domain for S alpha 1 inverse action. Okay. So then act by the S alpha 1 inverse, then you can obtain a X2. In the same method, you can obtain an S alpha 2 inverse and so on. Okay. So by like this, you can obtain a sequence of the elements of S, and you can obtain a sequence of points of lambda. So we say that this kind of sequence or the D delta code for X. Okay. So, and there are many choices for the S alpha, the 1, S alpha 2 inverse, and so on. So for each X, there are many, actually it might be the infinitely many, the D delta code for X. But anyway, so first start with the X, X1, X2, X3. So we have also the many sequences of elements of lambda. Okay. So what is the property of the delta code? So in each step, so S alpha I inverse action is a lambda expanding on here, right? D delta. So delta ball of the Xi. So this is expanding. So conversely, so this S alpha I action is contracting on delta ball of Xi plus 1. So that means that if you put back the delta ball of Xi plus 1, then this is contained in the, so delta over lambda, the ball of Xi. So this is contracting, lambda contracting. So this can happen all step. So then you can put back the delta ball to the X by using this whole, all the elements. Then this is the exponentially contracting on, so this the delta ball. Okay. And also we can show that this ball is nested. So because we have this delta ball xi plus 1 is contained in here by the S alpha I. And also, so by using the 1 over lambda contracting property, we can show that this delta ball over xi plus 1 is mapped to the inside of the lambda, the L delta over the lambda, the ball over xi, the x by the C alpha I. So we have so given some code, d delta code for x, we have some nested the exponential shrinking domain of some m. So, and also clearly by definition of code, so xi plus 1 is mapped to the x by C alpha I. So the domains contains x. So it's their intersection consists of just a point x. So that in this sense, we call the delta array encode the point x in lambda. Okay. So then we can prove that. So for each x, you can think of the set of all code d delta codes. Then the d delta codes turns out that some uniformly coded geodesic in calligraph. Okay, so we can always prove that this one without any condition, and also we require another condition, so-called the M-parallel traveling property. So d delta array, the two delta array are said to be an M-parallel travel. So if they are within the Hausdorff distance and from each other. So all the d delta arrays for the given x. So to M-parallel traveling, then we say that the action or the gamma action on lambda is M-parallel traveling. Okay. So that is the definition of the M-parallel traveling. So Sullivan proved that if the gamma action on the lambda is expanding and M-parallel traveling, then this action is structurally stable. So that means that if you have some hyperbolic action on some compact C1 manifold M, and with some action invariant the compact subset the lambda, so that means that it satisfies the expanding action and the M-parallel traveling property. So then every the sufficiently small perturbation of the action rho, then there is a rho prime invariant compact subset lambda prime nearby the lambda, and the topological conjugacy, the phi, from the lambda to lambda prime. So this is a homeomorphism between the rho action on lambda and rho prime action on lambda prime. So that means that if you perturb the hyperbolic action, you still get the same similar the hyperbolic group action, so nearby the original action. And also, he proved that any convex co-compact group on action on its rim set is a hyperbolic action in the sense of the Sullivan. So that means that the convex co-compact group action on its rim set satisfy the expanding action and the M-parallel traveling property. So what is the advantage of the Sullivan's approach? So actually, the convex co-compact representation is stable. We know in PSL2C. That means that if you have a convex co-compact group in PSL2C, if you perturb in the PSL2C, then you still get the convex co-compact group. But if you think of convex co-compact group action in the diffeomorphism of a sphere. So then still we can prove that by using the Sullivan's method. So the action on the S2 action is still stable, structurally stable. If you perturb the convex co-compact group action, perturb the in diffeomorphism group over S2, still you can get some nice invariant compact subset. And actually, so this action is rigid in the diffeomorphism group over S2. Okay, so this here is a proof. So actually, in convex co-compact group case, the proof is very easy, because the convex co-compact group action on the limit set are the expanding. So it is well known. And also the delta ray for the X corresponding to a uniformly cogeodesic ray in H3, hyperbolic n space, 3 space, toward the X. Then by using the geometry of the negatively the curved geometry, all the uniformly cogeodesic ray with the same endpoint is bounded away from, uniformly bounded away from to each other by the Morse lemma. So that gives the M-Ferro traveling property. So we can prove that the convex co-compact groups are the hyperbolic action in the sense of the Sullivan. So M-Ferro traveling property actually comes from the Morse lemma in hyperbolic space.
The ray.
Yeah, ray in Caliban. But you can prove that the ray is also the uniformly cogeodesic ray in hyperbolic free space, because the convex co-compact group is Cauchy-isometrically embedded into the hyperbolic free space. So how to prove the stability of hyperbolic action in the sense of the Sullivan? So if you first, so here, this is idea. So the first start with some expansion data. So symmetric generic set and associated expanding the open covers and the lambda and L. So this is just the expanding factor, and this is some kind of research constants. So if you perturb a little, then you obtain the expansion data. Here, so S and U, we do not change this data. Because if you perturb a little, then by just adjusting the expanding factor and the Lipschitz constant, we can also prove that the perturbed action is expanding with respect to this data. Then for any the ray, so we have some nested the exponential shrinking domains. So here, but we perturb the action. So we don't know this is with respect to the perturbed action, we also use the data ball, okay, associated to the X. So then still the domain is still nested and the exponential shrinking. So that means that gives some point by using their intersection. But here the problem is this point maybe depend on the choice of the ray, so-called, for X. But the M-Ferro traveling property gives the well-definedness, the independence of the choice of the code. So actually, so we feel the details in. So he skipped this detailed the proof for this well-definedness, but we first feel the details for the proving this well-definedness. Okay, so this gives some map the phi from the lambda to some into the M. So actually, so this is the injective. We can prove the injective, the equivalent, and the continuous map. So that means that this is some homeomorphism onto its image. Okay, so we are done. So this is a story of the Sullivan for the hyperbolic group actions. So after filling the gap, his paper, filling the details in his his proof, we realized that his approach may be extended to the other action. So here are the further applications. We first applied to the anaspor representation. So anaspor representation is a kind of the generalization of a convex co-compact group to the in higher rank semisimple Lie groups. Anyway, so the proof is same. So here anaspor group action on its limit set in some flag space. So then this is a hyperbolic action in the sense of the Sullivan. So we can prove that the anaspor group action on its limit set C0 stable in some kind of research homeomorphism group of flag space. So this is the set of the homeomorphism groups with respect to some kind of the research topology. So two homeomorphisms are close to each other if their images cross and their ellipses constants are cross. And also the water hyperbolic group action there, the group boundary is are the hyperbolic in the sense of the ellipsis homeomorphism group of this group boundary. So this is the group hyperbolic group action on its group boundary C0 stable in the ellipsis homeomorphism group of the group boundary. So that means this is kind of resistive result. So if you perturb the little, but you have actually the same action. Okay.
What is
C0 stable means that there is some conjugacy between the two actions. There is some homeomorphism between two actions. So if you have okay, so here, okay, so here, so there is a homeomorphism between the two invariant compact invariant subsets. Okay. So after that, after some Mann and Manning and Weisman in 2022, they proved that so this group, the water hyperbolic group action on its group boundary is a C0 semi-stable in the homeomorphism group is a group boundary. So they dropped the ellipsis part. So that means that there exists a topological semi-conjugacy from the group boundary to the group boundary, the continuous equivalent, but the surjective map. But they also use the same technique of Sullivan. But they found some kind of expanding domain in the setting of the homeomorphism category, because we do not drop the ellipses because we use some expanding, some contracting the notion, but they found some similar notion in the homeomorphism C0 category. Okay, but they okay, yeah. So, but they do not. So by using the domain, the expanding domain, they can construct this surjective map, similar to the Sullivan's group. Okay, so this is next the study. So so far we just think of the order hyperbolic groups. So, but the next step is non-hyperbolic group actions. So because there are many try to find some group action having the stability, so but which is not the order hyperbolic group action. Okay, so for example, so the Fani and Garrito and Danzinger, they define some convex co-compact action in real projective space, which may be not non-hyperbolic group action. And also, you can think of the co-compact lattice in hyperbolic higher rank Lie groups. So the Margulis super rigidity, we know that the co-compact lattice in higher rank semisimple Lie group is rigid, right? Then we can say, in other words, the co-compact lattice is stable in higher rank semisimple Lie group. So what about the extend some diffeomorphism of the flag space and homeomorphism of the flag space? Because this co-compact lattice acts on the here, right? The flag space. So there are, but these examples are not the order hyperbolic groups, but it has a stability. So we want to also develop the theory to the non-hyperbolic group actions. So here is beyond the hyperbolic groups. So we first realized that so M-Farrow-Cherubin property is a very specific property involving just the hyperbolic, the order hyperbolic groups. But how to weaken this M-Farrow-Cherubin property to study the non-hyperbolic group action? So this here is some idea. Actually, so this idea comes from some words, the Koji geodesic, introduced by the Kapovich and the Greiner and the Rip. Anyway, so first I will introduce the weaken the M-Farrow-Cherubin condition. So the first, we introduced the N equivalence on ray. So first, the M-Farrow-Cherubin property requires the two rays, the Hausdorff distance of the two rays is bounded from uniformly bounded away, right? But we require just the infinite subset of the two rays, so within Hausdorff distance and from each other. So picture looks like this. So this is a C alpha. This is a ray. This is a C beta is another ray. So it might be go around like this. These two rays maybe not bounded by some uniform distance, but here you can find some infinite many points, so which are the within the Hausdorff distance and from each other. So we first define the N, so N equivalence on ray first. But because actually, so this condition is enough to prove the well-definedness of phi as before. Okay. And also we prove by using this weakened condition, we define a weakened M-Farrow-Cherubin condition, so-called the meandering the hyperbolicity. So because so this picture looks like a meandering something like that. So anyway, if you have a two ray, we define an N equivalence if there exists some interpolating the ray with respect to some kind of refinement of the expansion data. So C alpha is equivalent to the C beta, by interpolating some rays. Okay. So we say that if C alpha C beta is N equivalent like this, then we say that C alpha and C beta are D delta N equivalent. Okay. So this is the meandering-hyperbolicity in the generalizing the n-parallel traveling the property. Okay, so we define the action is a meandering-hyperbolic. So first, the action is expanding, and second, so n equivalent on rays. Then you can prove that the whole thing as the Sullivan's the proof, and also we can prove that the well-definedness of female, because the n equivalent n-parallel traveling property is essential in proving the well-definedness of the phi, right? But so n equivalence is enough to prove the well-definedness of phi, independence of the ray. Okay, so the action is a meandering-hyperbolic, which means that expanding and equivalence. Then this action is a C0 stable in Lipschitz homeomorphism group. So that means that there exists equivalent homeomorphism between the two actions. Okay, so what is key idea? As I told you, the n equivalence gives the well-definedness. Okay, so this is a very technical proof. So you just skip the proof. But anyway, so this is a key idea. Okay, so this weakened condition is a very so we did not realize that the condition gives some interesting examples. So, but we realized that the co-compact lattice in semi-simple regroup. So there is an action. So co-compact lattice action on the flag space satisfy these two conditions. Okay, so this is a quite surprising result to us, because we just try to understand the n-parallel traveling the property, but we found some interesting the theorem. So that means that the co-compact lattice in higher rank action on the flag space is a meandering-hyperbolic. So this action is a C0 stable in the Lipschitz homeomorphism of each flag space. Okay, if you perturb a little the co-compact lattice action on the flag space, you still get the same action on flag space. So proof. So here's proof. So proof is actually key point is to prove that the action satisfy the n equivalence. The n equivalence condition. That means that if you for any two rays, there exists some interpolating the ray, which is equivalent to the two rays. So how to define this one? Actually, if you have a delta ray, okay, so here, so this is the idea. So the co-compact lattice action on the flag space is expanding. So this is quite easy, and you fix some point in a flag in the flag space, then you can get out the ray, right, by using some expanding data. Then we can prove that this ray is the uniformly Morse quasi-geodesic. So uniformly quasi-geodesic is so here is picture. This is the wall is a singular rejection in the higher rank symmetric space. So the Morse quasi-geodesic, the ray is some the quasi-geodesic ray, the uniformly linearly away from the wall. You can think of that. So then you have the Morse uniformly Morse code geodesic ray for each the ray for given the point in flag space. But the two ray looks like this because the uniformly Morse code geodesic ray so cannot be, I mean, bounded by I mean, the Hausdorff distance of the two rays uniformly Morse code geodesic are not bounded away to each other. But so but you can find some enlarging some Morse data associated to the Morse code geodesic ray. You can find the interpolating the Morse code geodesic ray. So this is the key idea to prove prove that the co-compact lattice in higher rank the action on the flag space satisfy the N equivalence. So you can construct the interpolating the Morse code geodesic ray by adjusting the Morse data. Okay. Okay. So and then so this is also the interesting theorem. So after that, the Cornell, Strom, Norman, and the Spaghier, their group also proved this action, the co-compact lattice action in on flag space is a C0 semi-stable in homomorphism group of the flag space. So they also dropped the ellipsis the condition, but their technique depends on the technique of the Zimmer's program. So they are totally different the viewpoint. So anyway, so here similar the theorem to the Manning and the Weismann the theorem for the hyperbolic group action on growth boundary. Okay, so next, so this is ongoing the project. So actually, we want to prove. Actually, we want to explore this meandering-hyperbolic group action. So apply to the real projective space. So as I told you, there is a concept of convex co-compact groups in real projective space. So which is maybe not non-hyperbolic. Okay. So here is a setup. This is the first step. So this the gamma acts on the convex perfect convex domain in the projective space. So and the gamma omega is supposed to be a rank 1 divisible. So there is some rigidity theorem for the divisible domain. So higher rank case. So actually, the higher rank case is the symmetric space, higher rank symmetric space. Okay. So we just think of first start with the rank 1 divisible domain. Then what is a good domain associated to the omega on which the action is expanding and maybe more M-ferro traveling and N equivalent. Because the convex co-compact action in real projective space is also stable. So we want to see this action is that action does satisfy some kind of the hyperbolic action or the meandering hyperbolic action. Because if you think of the co-compact lattice of SL3R, so that acts on some convex domain, right? So if you think of the symmetric space associated to the SL3R as some convex domain in RP5, right? So that also the action turns out to be the meandering-hyperbolic, then there are some possibility that the convex compact group action in real projective space satisfying the meandering-hyperbolicity. So we try to figure out that. Anyway, so here is an example. So this is a torus, the projective torus. So like this, defined by like this. Then we just take the 3 points as the invariant subset, invariant complex subset. Then this is and take here UA for expanding domain for A. So this is an expanding domain for B inverse. This is an expanding domain for B. And take UA inverse to be the empty set. Okay. Then this action is meandering-hyperbolic. Actually, it's hyperbolic because so the red points are invariant under all elements of the group gamma. So for example, for the E1, there are only four the rays associated to this point. So and also you can prove that they are the M-Farrell traveling because they are just a finite. So this action is actually the hyperbolic action in the sense of the Sullivan. So that means that if you perturb this one, then you can still get out this action like this. Okay. So this is the basic examples for studying the convex co-compact group action in the real projective geometry. So, but here, what is the problem? So find given the convex co-compact the action on the convex domain, then find the gamma invariant complex subset lambda. So which is expanding and M-Farrell traveling or n equivalent. Okay. But as you know, there are some canonical boundary of the Catch-Arrow space. So for hyperbolic group, there is the group boundary is the canonical boundary. But the Catch-Arrow group, for example, Catch-Arrow group, there are no canonical boundary of group. So there are many. You can think of there are many the boundary, the action of so this gamma. So candidates for the lambda is first, you can think of the set of the proximal limit points. But in rank 1 case, rank 1 divisible the domain, this proximal, the limit set is equal to actually the particular boundary of the projective domain, convex domain. So this is not good. So because the Venua examples, there are many triangles, the torus triangle, the inside. So we cannot imagine the boundary, every boundary point to satisfy the M-Farrell traveling or the n equivalent. Okay. So my expectation is that this is not good. Okay. But second, you can think of the Morse boundary or the contracting boundary, the inside the ideal boundary of the convex domain. So because so here the Morse boundary and the contracting boundary is a kind of expanding the gamma action here the action is expanding. So this is a good candidate, but problem is this is not compact. The Morse boundary is not compact. So and also this is a subset of the ideal boundary. So this ideal boundary is not coincide with actually some topological boundary of a convex domain. So as here, so this boundary is not the ideal boundary of this domain, okay? Because actually, so these 3 points, so ideal boundary are concentrated on these 3 points, because the ray is actually so So this face, so line, the facing the face are actually the equivalent, under the Hausdorff distance. So that is that makes the difficult to study some Morse boundary of the contracting boundary of the convex domain. Okay, and third is the looking at some limit set in the flat space. Okay, I think this one is a more reasonable thing, but I don't know the Morse boundary of the convex domain and the contracting boundary of Morse the convex domain. So it is I think worth to study this kind of the boundary of convex domain, because here, so we know that if the Hilbert geometry has a rank one case, the Morse boundary is non-empty. So that means that there are something, right? But anyway, but this is not compact. But we don't know what is the Morse boundary of the rank one, the divisible the domain. So if we think of if we describe the boundary, then we may test the action on the Morse boundary is hyperbolic or the meandering-hyperbolic, the group action. Okay, so thank you for your attention. Yeah.